After studying this module, you shall be able to know metal-metal bonds, that is single, double, triple and quadruple bonds, low formal oxidation states, large energy of atomization, effective overlapping of atomic orbitals that favor the formation of metal-metal bonds, refractory metals like zinc, niobium, molybdenum, technetium, ruthenium, rhodium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, and platinum that have the greatest tendency to form metal clusters. Outermost d orbitals that participate in the formation of metal-metal bonds. D orbitals that combine to form not only sigma and pi bonds but also delta bonds are formed. The order of increasing energy of the molecular orbitals is sigma, pi, delta, delta star, pi star, sigma star. Learn types of metal-metal bonds. Analyze spectroscopic evidences for the presence of metal-metal bond. Metal-metal bond is a bond between two metal centers, particularly between two transition metal atoms, which ranges from a single to a quadruple bond. The existence of metal-metal bond is mainly because of the presence of n plus 1s, n plus 1p and nd orbitals as valence shell electronic configuration. The transition metals can form three general types of bonds such as covalent bonds, dative bonds, and weak metal-metal symmetry interactions, where covalent bonds being the strongest and the symmetry interactions are the weakest. The compounds containing a large number of metal-metal bonds forming triangular and larger structures are called cluster compounds. However, these also include linear MM bonds. The metal clusters can also be defined as any entity that contains a metal-metal bond. The journey started with the identification of the Mercury-Mercury bond in the Hg2 2 plus ion Hg2Cl2, which was the first D-block metal-metal bonded species. Most of these cluster compounds are homometallic. However, there are few exceptions with heterometallic cluster complexes. Some examples of clusters are shown for reference. Now we shall have a look at the classification of metal clusters. Metal clusters have been classified into two major categories. The polynuclear carbonyl, nitrosyl, and related clusters can be categorized as Class 1. These clusters are mainly formed by metals in their low oxidation states such as +1 and -1, which include the metal ions residing on the right-hand side of the periodic table. The other category, Class 2, includes clusters formed as halides and oxides of transition metal complexes in their higher oxidation states. The transition metals lying on the left-hand side of the periodic table, the second or the third row transition metals, form such type of cluster compounds. For example, the Re2Cl8 whole 2- cluster contains a rhenium-rhenium single bond with +3 oxidation state on each rhenium center in the cluster. Criteria for metal cluster formation is as follows. There is a general trend that transition metals having large energies of atomization such as zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, and platinum display higher tendency to form metal clusters. Nature of the d orbital. The effective nuclear charge is inversely related to the size of the d orbital. Higher the nuclear charge tends to reduce the effective overlap of the d orbitals, which is unfavorable for cluster formation. For example, the first row transition metals with higher oxidation states such as +2 and +3 do not offer sufficient orbital overlap and therefore poses an unfavorable situation towards cluster formation. Now, we will look at the metal-metal bonding in metal clusters. There are three major types of bonding in metal cluster. Number one is the covalent bonding. One electron from each metal atom constitutes a single metal-metal bond between the two metal atoms. This is the most common type of metal-metal bond, ranging from a single to a quadruple metal-metal bond. Molecular orbital theory can be used to explain the overlap of various orbitals to form three types of bonds, namely the sigma bond, pi bond, and the recently introduced delta bond or the quadruple bond. Considering the possible overlap between the d orbitals on adjacent metal atoms, one can figure out that a sigma bond between two atoms is a result of the overlap of dz square orbital from each atom. Two pi bonds can be formed by the overlap of the dzx and dyz orbitals. Two delta bonds can arise from the two face-to-face overlap of dxy and dx square minus y square orbitals. The dx square minus y square orbital is also utilized for bonding with ligands. The energy diagram shown here points towards the possibility of a quintuple bond, which could result when all the bonding orbitals are occupied to give an electronic configuration of sigma 2 pi 4 delta 4. Examples of multiple bonds containing metal clusters are as follows. The table shown is based on the criteria for cluster formation. As the number of electrons increases, the possibility of formation of higher number of bonds between the two metal atoms increases. If the number of d electron involved goes beyond 8, the electrons go to the antibonding orbitals and hence the number of bonds tend to decrease. In a case where the metal atoms having d8 or d10 electronic configurations are involved, there is practically no chance of bond formation between the two metal atoms due to filling of anti-bonding orbitals. The table is as where the electron count, if it's d1, it results in the formation of single bond electron count. When it is d2, it gives rise to a double bond. d3 gives triple bond. d4 gives quadruple bond, which is optimum, and d5 gives triple bond. d6 electron count gives double bond. ML bonding usually dominates here. d7 gives single bond, and d8 electron counts gives no bond as per the symmetry interaction. The second type of bond is the dative bond. This type of bond is formed when one metal having filled d orbitals coordinates to a metal atom containing empty d orbitals by the donation of a lone pair of electrons. Dative bonds are represented by an arrow instead of a line, starting from the donor metal and pointing to the undaturated metal atom. The bimetallic nickel complex has one dative bond. In this complex, the nickel-nickel distance is 2.41 angstroms. The donor nickel has a D10 electronic configuration, whereas the acceptor nickel has a D8 electronic configuration. That is, it is in the Ni2+ state. The third type of bonding is the weak metal-metal symmetry interactions. The weak metal-metal symmetry interactions are a result of symmetrical overlap of molecular orbital. This overlap is generally between filled and empty metal-metal bonding and or antibonding orbitals. These interactions are typically seen in few bi- or polymetallic D8 complexes, both in solution and in the solid state. For example, the iridium tetrakis isocyanide complexes form oligomeric chains through MM interacted stacks in solution and in the solid state without showing any evidence of a metal-metal covalent bond. These interactions were initially studied by Harry Gray, who proposed that these interactions are caused by a molecular orbital symmetry interaction between the filled orbitals and the empty antibonding molecular orbitals. Now, we shall have a look at the factors favoring the formation of MM bonding. Metal-metal bonds are mainly formed by transition metal ions and not formed by all the metal ions. The metal ions that has the ability to form single or multiple metal-metal bonds, either homometallic or heterometallic, do so under particular situations. The number and the type of metal-metal bonds in a particular metal cluster depends on various factors. Few important factors that govern the formation of metal-metal ion are position of the metal in the periodic table, its oxidation state of the metal ion, and the types of ligands attached. The most important factor that directs the formation of a metal-metal bond is the low formal oxidation state of metal ions willing to form a metal-metal bond. For example, the alkali and alkaline earth metals have very low ionization energy and they are able to show high oxidation states. Hence, most of these metals exhibit ionic bonding with a very little scope for a direct covalent metal-metal interaction. However, there are few exceptions with lithium, beryllium, and magnesium. The dimagnesium complex shown as a magnesium-magnesium single covalent bond. Here Ar stands for 2,6-diisopropyl phenyl. The formation of metal-metal bond depends on metal-metal orbital overlap to a large extent. The low oxidation state of the metal ions allows sufficient overlap of the metal valence shell orbitals, favoring the formation of metal-metal bond. The metal clusters with low formal oxidation of metal ion generally exist as carbonyls, nitrosyls, and related compounds, where the higher oxidation state metal clusters exist as halides and oxides. Another important factor that favors the formation of metal-metal bond is the stability of the valence shell. The metal-metal bond distance should be decreased, which is opposed by two factors such as increasing atomic co-repulsions and ligand-ligand repulsions. It is known that the atomic co-repulsions are comparatively higher in 3D metal ions than in 4D or 5D metals. Hence, the first row transition metals do not form metal-metal bonds in higher oxidation states but form in a low oxidation state. One of the important factors that affect the formation of the metal-metal bond, particularly in transition metal complexes, is the nature of d orbitals. The size of the valence orbital is inversely proportional to its effective nuclear charge. Excessive effective nuclear charge would allow the contraction of the d orbitals and therefore lesser overlap of the orbitals, which in turn destabilizes the metal cluster. For the extreme left transition metals, the d orbitals are relatively smaller in lower oxidation states such as +2 or +3. Therefore, the d orbitals in the early transition metals are ineffective to form a good orbital overlap. Now, we shall see the infrared spectra of metal-metal bonded clusters. Metal-metal clusters contain metal-metal bonds and few of the complexes display characteristic infrared absorption patterns. The constituent ligands and their bonding patterns can also be identified by infrared absorption. However, only the infrared absorption data is not sufficient to elucidate the complete structure of the cluster compound. Therefore, IR data must be combined with other studies such as X-ray diffraction analysis, mass spectrometry, nuclear magnetic resonance, and Raman spectroscopy, etc. For example, the metal carbonyl complexes display a variety of bonding modes as shown in the figure. These bonding modes can be distinguished and identified by vibrational stretching bands of carbonyl groups in infrared absorption spectroscopy. The structure 1 is called semi-bridging, can be assigned to bands at 1871 and 1831 centimeter inverse. The semi-triple bridging bonding mode, that is 2, displays infrared band at 1693 centimeter inverse. whereas the other semi-triple bridging bonding mode 3 displays much weaker carbonyl stretching vibrations at about 1330 centimeter inverse. Generally, the metal-metal bond vibrational frequencies appear in the low frequency region, that is from 25 to 100 centimeter inverse, because the metal-metal bonds are relatively weaker. However, various metal clusters have high vibrational frequency of about 400 centimeter inverse because of the multiple bond character of the MM bond. Moreover, the centrosymmetric MM bonds are IR inactive, but the heteronuclear complexes are IR active. In contrast, the Raman spectroscopy cannot distinguish between homonuclear and heteronuclear MM bonds due to large changes in polarizabilities as a result of MM stretching. For example, MM bond distance in MO2 OAC4 is 2.09 angstroms and displays stretching frequency at 406 centimeter inverse. This MO-MO bond, this consists of a 1 sigma bond, 2 pi bonds and a delta bond. The rhenium-rhenium quadruple bond of Re2Cl8 2- shows stretching vibrations at 272 centimeter inverse. Trinuclear complexes such as M3 carbonyl 12, repeat, such as M3CO12, where M can be ruthenium or cobalt, possess triangular skeleton for which 2 mm bond stretching are expected under D3H symmetry. The ruthenium-ruthenium bond vibrations in this complex were observed at 185 and 149 centimeter inverse. Now we shall study about the electronic spectra of metal-metal bonded clusters. On exposure to UV visible radiation, the metal cluster complexes undergo photoexcitation and some of them result in photochemical reactions. For example, the polynuclear metal carbonyl complexes contain metal-metal bonds and display photochemical reaction which lead to clean rupture of metal-metal interactions. Such kind of transformation results in the formation of paramagnetic organometallic complexes due to rupture of the metal-metal bond. The paramagnetic intermediates have odd number of electrons and are important stoichiometric and catalytic organometallic substrates. The photoexcitation of CO2-CN10 result in the formation of D7 17 electron COCN5 3 negative species having unpaired electrons and display reactions with alkyl halides, olefins and small molecules such as hydrogen, halogen and sulfur dioxide. Therefore, photoexcitation of metal cluster compounds results in the formation of excited state species and may also result in photolysis. Now we shall summarize what we have learned in this module. Multimetallic metal complexes possessing metal-metal bonds are called cluster compounds. There are a variety of geometries such as linear metal-metal bonds, triangular and larger. There can be homometallic as well as heterometallic metal-metal bonds. The metal cluster can be classified on the basis of oxidation state of the metal ion and the bonded ligands. For example, the metal clusters containing halides or oxides as ligands are generally formed by metals in their higher oxidation state. Metal clusters display mainly three types of bonds, namely covalent bonds, dative bonds, and weak metal-metal interactions. Among these, the covalent bond is the most prevalent one. The number and type of metal-metal bonds in a particular metal cluster depends on various factors such as the position of metal in the periodic table, its oxidation state of the metal ion, and the types of attached ligands. The compounds containing a large number of metal-metal bonds forming triangular and larger structures are called cluster compounds. However, these also include MM linear bonds. Most of these cluster compounds are homometallic. However, there are few exceptions with heterometallic cluster compounds. Metal clusters have been classified into two major categories: the polynuclear carbonyl, nitrosyl and related clusters, and the cluster formed as halides and oxides of transition metal complexes in their higher oxidation states. There are three major types of bonding in the metal cluster. Metal-metal clusters contain metal-metal bonds, and few of the complexes display characteristic infrared absorption patterns. The Raman spectroscopy cannot distinguish between homonuclear and heteronuclear bonds due to large changes in polarizabilities as a result of stretching. On exposure to UV visible radiation, the metal cluster complexes undergo photoexcitation, and some of them result in photochemical reactions such as the rupture of metal-metal bonds.